Alright, welcome everyone to another inequality video. So far on this playlist we've discussed two very important inequalities, which were the AMGM and the Cauchy's inequality. Of course, the Muirhead was just a branch of the AMGM. Right now you're qualified to solve many of the standard inequality problems and even some of the advanced IMO problems. However, we still need to discuss many other less important inequalities, but each one of them has its own applications. So in this video, we'll be discussing a kind of a generalization of the Cauchy's inequality, which is Holder's inequality. So before we get started, I want to remind you to join the Discord server. You can see it on the link below. In this server, you can, we have many activities. You can chat with other guys that have the same interests as you. And we're actually doing many papers, weekly papers. We're posting them there, so you can share your solutions and ask for help. So make sure you do that, and of course don't forget to subscribe to the channel here and like the video, turn on the notifications, and what are we waiting for? Let's get started. Alright, so let's get started with the Holder's inequality statement. So it's just a simple inequality. Let's just write it down. It's simply the pi, numbers from 1 till m, pi of the sum here, starting from 1 till n, of the sequence ai j. This thing is greater than or equal to the sum starting from 1 till n of the root degree m of the pi of a I j starting from 1 to m, and all of that to the power m. So as you can see, it's really simple inequality, and I'm pretty sure that you can immediately start to solve some inequality problems about it. Alright, you got me. It's not simple at all. So let's just take a special case and try to get rid of this scary theorem. But by the way, this is just the general Holder statement. Okay, let's just take a special case, and with this special case, hopefully you will understand what is happening. So let's say we have positive numbers. By the way, here the numbers are positive. I forgot to mention that. So here aij, all of them are positive. Okay, so the special case we'll be working with is the following. Let's write it down. a1 cube plus a2 cube plus a3 cube times b1 cube plus b2 cube plus b3 cube times c1 cube, c2 cube, c3 cube. This thing is greater than or equal to a1 b1 c1, a2 b2 c2, a3 b3 c3, all of that to the power 3. Alright, so now if you take a look at this thing looks nice. If you can do some elaboration here, you can see that what is happening is you have, of course, some of a cubes, some b cubes, some c cube. What we did is simply catch this thing, multiply these guys together and take the cubic root. So we get a1 b1 c1, and then we do the same thing, this times this times this, and we can take the cubic root, and same thing for the last one to get the last one. And after all of that, of course, we cube to make everything homogeneous. So this thing is degree 3, and here to the 3, so it's degree 9, and here degree 3, 3, 3, so it's 9. So as you can see, this is very similar to the Cauchy's inequality. In Cauchy we had something like this. square and b1 square, and we got a1 b1 all square. So here we just had two things. Of course, it was the same idea. We multiply these and take the square root. So literally here the same idea as Holder, but Cauchy we can only apply it on two brackets, as you can see, just two. We cannot do it on 3 or 4. So this is basically the main advantage of Holder. Holder is a generalization to Cauchy, because in Holder you can play not just even on 3, but even if you add other. So actually you can here add like another D sequence, and you can just do the same thing here, like D cubes, and you will just have here A1, B1, C1, D1. So this is the main advantage, as I told you, of Holder. It's just a generalization of Cauchy. Once you keep that in your mind, then you will see that everything looks really understandable. And now if you try to look at this scary thing again, you will kind of understand what's happening. So here, each sum represents one of these guys. We have a product because it's a product of sums. This is sum number 1, sum number 2, sum number 3. We're multiplying them. And what's happening is, instead like of the product, now we turned it into a sum, a single sum, all to the power m. And this sum here, like each what is this thing? We multiply all the numbers together, like this by this and this, and we take the cubic root here. So here, as you can see, this is why we have the mth root here. If you just like here substitute the numbers with power to the power m to the power m, you will get rid of the cubic root here, which of course will be more interesting, because in real life, like you don't want to get like some roots really. You want to get rid of the roots. So this is why usually you want to have something like this. So I hope now you understand the statement. As we said, the most important thing, keep in mind that Holder is just a generalization of Cauchy. And now we can continue. If you remember in Cauchy, when we discussed Cauchy's inequality, we said that we have like one version of it, which we called the Titu's lemma. Titu's lemma was something like this. For x, this thing is greater than or equal to sum of a all squared divided by sigma x, given that of course the x or all the denominators are positive. So the question is, do we have also a Titu's lemma for Holder, or no, it's just for Cauchy? Well, guess what? Indeed we have. Of course it's not called Titu's lemma, but it's kind of the same idea. So what exactly we can do here? We can write something like that. If we have sigma a cube divided by x, can we make like something perhaps like sigma a and sigma x? Well, yes, we can. Simply, if you want to do that, then just the same idea as how we derive Titu. I'm just going to multiply by sigma x here. Now, if I apply like this is bad, because I will have like a root, square root of the cube. So I need to add another one to make it Holder. So I will add sigma 1. This is like the standard trick. If we add sigma 1, now 1 times x times this thing will be just a cube. So now I will take the cubic root of it. So it's going to be just sigma a. And all of that will be cube. So that means this thing here is just, if we rearrange stuff, it's sigma a all cube divided by the sigma 1, don't forget it. Let's say like we're playing just with 3 numbers, then it will be 3 sigma x. But of course, if you're playing with more numbers, then you add, for example, you play with n numbers, then you put n, no problem. So basically, yes, we do have Titu's lemma for Holder. You can keep this in your mind, because usually when we play, we just have 3 numbers and cubic roots. But of course, you can generalize this to whatever you want, even if you have not just cubic root, even if you have here like a to the 5 or a to the n, then you can just multiply by sigma 1, sigma 1, sigma 1, many sigma 1s, and probably you'll get something like here n3 to the n minus 2. So you can from here always derive kind of Titu's lemmas for any n that's here. But of course, don't go to the like contest and try it by Tito's lemma, because no, this is not called Tito's lemma, but just to keep it in mind, it's very similar to the original Tito's lemma, or the angel form of Cauchy. Alright, so that means now we kind of understand what is holder. It's basically just a simple generalization, and we can even of Cauchy, and we can even generalize Tito as well. So now we should be comfortable to start working with some examples, and let's start simply by example 1. Alright, here is a very simple example. Let's say we have three positive numbers, and we need to prove the following inequality: pi of x squared plus y plus 1. This thing is symmetric, so we have all of the combinations of these guys. This thing is greater than or equal to sigma x to the power 6. That's it simply. As you can see, this thing is, of course, we have here 6 terms, and here we also have 6 terms. But is this homogeneous? Sure, no, because you can see degree 2, degree 1, degree 0, so this thing is not homogeneous. Alright, how exactly can we handle something like this? Of course, the fact that you are seeing a pi of sums, this should immediately remind you of holder or Cauchy, because you have literally the same like shape, something like that. And you can, with holder, like just mix them and turn them into a single bracket to some power. So this should immediately remind you of holder, and we can, like, in order to apply holder, we should try to write all of these guys, because otherwise it's very hard to keep that keep tracking them in your mind. So probably just if you write them, it's going to be a good idea. So let's start doing that. X squared plus y plus 1. Going to also have x squared plus z plus 1, y squared plus x plus 1, y squared plus z plus 1, z squared plus x plus 1, and z squared plus y plus 1. Alright, now we want to kind of combine these somehow to get the sigma x all to the 6. So let's try to think about that. If you want to apply holder on these guys, the 6 terms, then like you're going to have degree 6 root. So that means, of course, you don't want to have something like here x to the 5 or something. You should have x to the 6, right? So this thing should be what you're looking for. So we want to find a way to multiply these guys together to get something like x to the 6. So let's see, can we do that? Here we have x squared. Here we have x squared. Here we have an x. Here we have an x. So if you multiply that, x to the 4, x to the 6. Okay, exactly. So we should simply pair these guys together. But wait a minute, we are missing something here. What should we pick? Of course, you don't want to pick z nor y squared, so you should pick just 1, and here pick 1 as well. So in fact, we're already done, because we were able to get the x to the 6. So by holder, here you can just write holder. Immediately, we got sigma. First of all, you write the sigma, then x to the 6, and this under the roots of the 6th degree. So that means just sigma x. And of course, all of that to the power 6. So indeed, it was like a piece of cake. The same actually application is literally holder. In fact, this question, you can even solve it with Cauchy's inequality. Try to think about it and post your solution in the comments. It's really not hard to see it. You can just use Cauchy's here to get exactly the same result. But anyway, holder here is just literally the direct application of it. You'll be done. Okay. Let's take another example, and that will be it for this video. So example 2. Let's say you want to show a to the 6 divided by b squared plus c squared is greater than or equal to ABC times sigma A divided by 2, and of course here the numbers are positive. Okay, need to prove this. Okay, let's have a look at this. As you can see here, we have like a fraction, and as we know, Cauchy is very nice to handle fractions, and Holder is the same as Cauchy generalization, so of course it's also very nice to apply it on fractions, to get rid of fractions, or basically to clear the denominators. Okay, so how can we clear these denominators here? Of course, usually we apply Titu in these types of situations. So here actually we have the idea of just applying the regular Titu. So you can just say that the LHS is greater than or equal to sigma A cube all squared divided by 2 sigma A squared. And this thing looks nice. You can of course now apply this by this here, and just try to show like that. In fact, if you do that, you'll be able to solve the question. So yes, indeed, Cauchy Titu here, the regular Titu works. But can we actually do it in another way? Well, of course we can. The other way that we want to do this is to try to apply the same Titu, but the Titu for Holder. Because here we have to the 6, right? So we can make it a square cube. What does that mean? I'll just now apply the version for, this one, this version. Remember, if you have like a cube, then you can also make it like this shape. So let's try to do this. I mean, like literally, I'll be doing the same thing exactly by applying this one, of course, the regular Titu. Let's write it here, like regular. But now if we apply the kind of Holder Titu, then it will be sigma A square cube divided by, don't forget the 3, and we have actually that here. If we add these guys, we get 2 sigma A square, so it's actually 6 sigma A square. Now the nice thing is here we had cube and sigma A square, but here we had sigma A square and sigma A square, so they cancel. So in fact you just get something much easier to work with. It's just sigma A square divided by 6. This thing is for sure easier to work with, although as I told you, both of them work. You can solve it with both of them by just now expanding and probably applying Muir head. So now what we want to show is we want to show this guy here is greater than this thing here. It's actually well known that sigma A squared is greater than 3abc sigma A. Of course, to prove this, it should be a piece of cake for you right now. If you've been following the playlist, you just expand like this and expand this as well. And one idea is that this thing is sequence 4 0 0, this thing is 2 2 0, and this thing is 2 1 1. So of course both of these guys majorize this, so you can just apply Muir head and you're done. Yeah, that's it. Basically you can actually show this in another way, which is like kind of easier. If you remember, we know that sigma x square is greater than 3 sigma x1. This thing you should keep it in mind. Of course, we discussed that in the AMGM lesson. So now if you apply the same thing but you substituted x as a square, you are just going to get this thing here, like a square. Wait, is it really a square b square? Oh wait, no. Wait, a square bc. I don't think this one works here. Yeah, probably it doesn't work. I think I messed it up with yes, with this. Now I see. If you have sigma a square b square and you want to link it to this thing here, like if you have something like this, yeah, now you can do this thing actually. So the idea is the same here. If you plug x as AB, and now you applied it, you're going to get AB times BC, or like BC times AB times AC. So now this thing is correct, but here you have a 3. So that means you can replace this with this. And guess what? We know that sigma AB is less than sigma A square, so this one works. So this is just another solution to this one. Or you just can expand, because this thing is really a piece of cake, and use mu heads for it. So the main idea here was you just apply Titu, either the regular Titu or the Holder Titu. Holder Titu here is just a nicer one because you just get sigma A square all squared. You don't have like cube and A square. So here it is. You can see that literally a Holder is just a generalization for Cauchy. Yeah, that's it. Alright, so as a summary, we see that Holder's inequality is just a nice generalization for Cauchy, and you can see that this scary thing here is really not scary at all if you just remember the special case, and keep in mind that it's literally Cauchy, but generalized one. Do we have Titu for Holder? Yes, we do. You can see that we can generalize it easily, and here we just solved two simple examples. The first one was to show you that you of course always want to avoid roots. So how do we get rid of roots? We should pick it, for example here, to the power 6. So we should of course take all the x's alone and pick the ones when there is no x. The other example was to show you that just like Cauchy clears denominators, then so does Holder. You can also clear denominators with it, either by applying Holder or by applying just the Titu form of Holder, both of them like clear denominators. Alright, so that's it for today, my friend. In the next video, we'll be discussing much more advanced problems about Holder, and we will see that Holder is not just a generalization for Cauchy. Sometimes some problems cannot be solved with Cauchy, like this, like problem 2. Sometimes you have to use Holder to solve some like IMO problems. So Holder definitely is a very important inequality to keep in mind. So don't forget, guys, to post your solution for the first problem using Cauchy in the comments below, and don't forget to join the Discord, and like, share and subscribe to my channel, and see you guys in the next video.